session window here. So here's my r-squared value. And what I'm going to do is I'm just going to briefly discuss what r-squared represents. So r-squared is called the coefficient of determination. What's surprising about r-squared is that, and I know this is obvious to you all, but it's actually the square of this quantity here, which is your correlation coefficient. But what's a little counterintuitive is that your r value, which is a number between -1 and 1, when you square it, you actually get this r-squared value, which, and if you see right here, is actually given in percentage. And I wanted to talk about that, why when you see r-squared, which is just a square of your correlation, why you get a fraction or why you get a percentage. And that's pretty key to doing this. The other thing is that notice in Minitab, nowhere are you given the correlation. You're just given r-squared and you're given r-squared adjusted. So I think that that's kind of interesting too. Minitab doesn't, it's not that it doesn't care about correlation, but for some reason it thinks to give you the r-squared value and not the r value. So I think that that bears some mentioning too. Okay, so recall that when we're looking at this quantity r, the 1 over n minus 1 is going to be this fudge factor that's going to help us scale things. Your xi minus x bar over sx is your scaled score. Your x bar is the average in the x direction or the horizontal direction, and your sx here is your standard deviation of your x variable. So we're going to multiply the deviance in the x direction times the deviance in the y direction, and then scale those values by the corresponding standard deviations. And we talked about that on Friday of last week. Okay. Oh, rather Monday. Okay. So here's the picture that we have. So remember, when we're doing regression, the least squared regression line, which is this quantity here, f, the least squared regression line is obtained by minimizing the sum of the squares of these blue, the sum of the areas of these blue squares. Okay, that's why we call the least squares regression line the line of least squares. It's because we're trying to minimize the sum of the total areas of these blue boxes. Okay, so what we're doing when we're calculating r-squared is we're making a comparison between the blue boxes and the red boxes here. Okay, so what are these red boxes? So the red boxes represent the error if you were to take the y coordinate. So notice how, let me just pause here for a minute and just explain. By looking at these two graphs here, the one with the red squares and the one with the blue squares, notice that the y position of these graphs are the same. Okay? So this is not a residual graph. Just bear with me for a minute. Here we have y bar. So y bar, if I just bring this out here, y bar represents the average in the y direction. So if we just take the y values of the actual numbers here and we average them out, we get this horizontal line. So this horizontal line is a line that associates the data. Just like your regression line is a prediction equation, the y average could also function as a prediction equation. So what we're doing here when we're calculating the red squares, so here's one red square that represents the square of the difference between y average and the y actual for this point. If we take the second point, we get this other red square. So here's the other square from the actual value to the average in the y direction. So if we take the sum of these squares, we're also going to get a sum of areas. And what we want to do is we want to compare how the average in the y direction is relative to the prediction line or the least squares regression line. So in other words, which is a better predictor? Is it the regression line or is it the line that's represented by the averages in the y direction? So the way that we're going to do this analysis is we're going to look at this quantity here on the left. So SSRES represents the sum of the squares of the residuals. So that's going to be, if you just look here at this bottom equation, I'll actually bring this bottom equation, let's see if I can bring it up top here. Yeah. So SSRES is going to represent the difference between the actual value and FI, which is just what we're calling here. I actually grabbed this from Wikipedia. What we're calling the regression line. So these yi minus fi's are just the residual values, but then you're going to square them. And then SS tot here is going to be the sum of the squares of the total area relative to the average y bar. So SS tot here is just going to represent the area of the sum of the total areas of these squares, red squares. So if you look at this fraction, SSRES divided by SS tot, that's going to give you the fraction. So you subtract 1 minus that, and I think this is somewhat magical, you can actually show this out mathematically, that R, so Pearson's correlation coefficient, is actually equal to 1 minus this fraction. So going back to how Minitab reports R squared, it does make sense now because R squared can be shown mathematically to be 1 minus the ratio of the sum of the squares of the residuals divided by the sum of the squares of the deviance from the average in the y direction. Because it could be represented as that fraction, it makes sense then to represent R squared then in terms of a fraction or a percent. R squared adjusted is just another way of giving you information about the fit of your data, but it's communicating also that there's something unknown about your population. That is, R squared adjusted is very similar to R squared, except for the fact that it takes into account that there could be some error in the way that we've computed the population. So R squared might be a little bit smaller than your R squared value, but R squared is never greater than your R squared value. Lastly, it's helpful here to just note again that R squared is a fraction and often denoted by percent, and R squared represents the fraction of variation in the y or response that is explained by regression of y on x. So just some explanation here. So here we have R squared represents the fraction of variation. So what we're saying here is that fraction of variation is just the variation relative to how the residual values are to the values in the sum of the squares of the y average. So let's just talk about R squared for a minute. If R squared is equal to 1, that means that, so let's just write this out here. Well, if r squared is equal to 1, that means that this quantity here is equal to 0. So what that means is that the sum of the squares of the residuals is equal to 0. Or the numerator here is equal to 0, because the denominator can't be equal to 0. So when the numerator is equal to 0, that means that the sum of the squares of the residual values is equal to 0. So in other words, yi minus fi is always equal to 0. Well, that's only going to be the case if these points are collinear. Well, if the points are collinear, we would expect that the correlation is equal to 1 or negative 1. And when we square negative 1 or positive 1, we're still going to get 1. R squared could also equal 0. Well, if r squared equals 0, that means that the sum of the squares of the residuals divided by the sum of the squares of the total area for the red boxes here, this entire fraction is equal to 1. Well, if this entire fraction is equal to 1, that means that the sum of the squares of the residuals, or these blue boxes, are no better a predictor than than these boxes here in red. So again, these blue boxes here are the regression equation here is no better a predictor than this average line. Well, if the regression equation is no better a predictor than this average line, why don't we just choose this average here, or this equation here, to be our prediction equation? So r squared represents the fraction of variation in the y response that is explained by regression of y on x. So that means that if r squared is equal to 0, the fraction of variation that is explained by regression, or let's even say here least squares regression, if r squared equals 0, then 0% of variation in y is explained by least squares regression. If r squared equals 1, then 100% of variation in the y direction is explained by least squares regression. So what happens if we find a number in the middle? Like, say r squared is equal to 72.7%. Well, that means that according to this model here, where we were looking at waste versus weight, 72.7% of the variation in weight measured in pounds is explained by least squares regression of weight on waste in inches. So what about the other 27.3%? So what about the other 27.3%? What explains that? So 27.3% is 100%. Sorry, I know you guys know this is obvious, but I'm just going to write this out for instructional purposes. So we took the r squared value, subtracted that from 100, got 27.3%. So what explains that? Okay, so we're not sure. Our model only accounts for 72.7%. There may be a better model out there that has a stronger r squared value. It could be a polynomial fit, could be a logarithmic fit, an exponential fit.